Hello, Alg2Geo students. This is lesson 1, video 1. Today we are going to be discussing the basics of functions. There's a good chance that some of this is review to you. You've probably heard the word function used in the context of mathematics before, but it's really important. Some of you are sophomores, some of you are freshmen, and it is going to be important for the rest of your high school career, and if you do anything science or math related in the future, that you understand how functions work. So they're actually not that complicated in concept, but they can be more complicated. We can make them more complicated. But basically, a function is it's a correspondence between two sets. That's basically all it is. It's a specific kind of correspondence. And in technical math terms, we call a function that specifically, it's like a mapping. I don't want you guys to worry about that word. But basically there are two sets, the domain and range. Such that each domain value corresponds to exactly one range value. I say value, they don't actually have to be values. Maybe I should say this. Each item in the domain. When I say value, it means, I feel like you guys are going to assume that means that it has to be numbers, but it doesn't. The things in the domain and range can be anything that we want them to be. So I'm just going to say item. And they're normally going to be numbers, but I don't want you guys to get too tied up in that. We're going to talk about some today that aren't numbers, but so basically for everything you just have two sets of things. That means like a set is just like a group. So there's like a group of people and a group of dates, and a function could like connect those people to those dates. So for example, if there's 250 kids at Weber and then 250 birthdays, the connection between students at Weber and their birthdays is a function, because every person, every item in the domain corresponds to exactly one item in the range. So every person has exactly one birthday, because you know that no one has two birthdays. That doesn't make any sense. So that's an example of one where they're not just numbers, they're people and dates. So basically what the function does is it connects the domain. Like here, let's say this is the domain. This like bubble represents the set of all the things in the domain. And this bubble represents the set of all the things in the range. And the function, which we often call functions f, you can call them whatever you want. The function f connects the domain to the range. And it connects it in such a way that everything in the domain connects to only one thing in the range. There's a question like, well, can two things in the domain go to the same thing in the range? And the answer to that is sure, and that's still considered to be a function. So let's say I've got like Alice and Betty and Clarissa and Devin. And these are 4 people, and there's like 4 dates over here, like March 12th and April 17th and August 5th and December 10th. And let's say Alice was born on March 12th, so the function that matches people to their birthdays would match Alice to this. So let's say Betty was born on August 5th, so this would connect her. And let's say Clarissa was born on April 17th, so that would go here. Like, what if Devin was born on August 5th also, which I'm sure you all know two people with the same birthday? Then she would also connect to that same place here. Oh my Lord, try that again. She would also connect here. And the question is this still a function? And the answer is yes, this is a function. And if you go back and look at the definition, it's very specific that it's just, it's only that you can't have two arrows coming out of one domain item, but you can have two arrows going to the same range item. That's fine. If this was the case, technically, I feel like this wouldn't be in the range because nothing connects to it, but that doesn't really matter. The range can be all the numbers if you want it to be. We're not going to get too specific with that today. So that's the basic definition of a function. Correspondence between a domain and a range, and every item in the domain connects to exactly one item in the range and no less. Or sorry, no more than that. Okay, can't have two things. So are these correspondences functions? So the answer, matching a person with his or her weight. So is this a function? Well, ask yourself, can a person have more than one weight? Well, over the course of like a year or a month or a year or 10 years, the answer is yes, but at any given moment, every person has exactly one weight. To a good approximation, you can say, I weigh 175 pounds, and that's, I don't weigh 275 pounds, I don't weigh 75 pounds, I weigh 175 pounds. So is this a function? Yes. The domain of this function is the people we're talking about. Like I could have been more specific. I said correspondence matching Weber students, and then the domain would be all Weber students. And the range here would be weights, like numbers like 175 pounds or 110 pounds or however much people weigh. So this is a function, and the domain is all the people, and the range is all of their weights, whatever they happen to be. Here's another example. The correspondence matching the numbers -2, 1, 0, and 2 with each number square. So this might be helpful to write down. So here's the domain is -2, 0, 1, and 2. And the square of -2 is 4, and the square of 0 is 0, and the square of 1 is 1. And the square of 2 is also 4. So I don't have to write that again here in the range, so I've already got it. In general, we don't really want these numbers to repeat. So this corresponds here, and this corresponds here, and this corresponds here, and this corresponds there. Like we said before, it's okay if two domain values go to the same range, as long as one domain doesn't go to two ranges. So this is a function. And I would say that the domain is the set of numbers. We usually use curly braces for that. -2, 0, 1, and 2. And the range is just these other three numbers, 0, 1, and 4. You write that again because it's super messy. 0, 1, and 4. And I don't know, it doesn't matter. I rewrote these in numerical order. It doesn't matter if you had it or not, but I tend to. So right. So that is a function. And that kind of makes sense when you think about it. Like when you square a number, you only ever get one other number. Like if I square 7, I get 49 every time I square it. I can't square 7 and get some number other than 49. I can square -7 and also get 49, but that's a different domain value. Just the same way that -2 and 2 both gave me 4, but I'm never going to get anything except 4 when I square -2. I'm never getting anything except 1 when I square 1, and so on and so forth. That's why this is a function. So matching a best-selling author with the title of books written by that author. I don't know if y'all think an example would be helpful here. It might be. How about J.K. Rowling? She's a best-selling author, right? And so some of the books that she's written are Harry Potter and the Sorcerer's Stone. She wrote Harry Potter and the Goblet of Fire. Goblet of Fire. She wrote Harry Potter and the Prisoner of Azkaban, and so on and so forth. And so if I was going to match this author's name with these books that were written, I'd do this. Like every book on the list is going to get an arrow from J.K. Rowling. And the answer is, therefore, this is not a function. Because that one domain value, which in this case was J.K. Rowling, but in the general case is just a name of any author. Because like every range value was generated by that one domain value. I am calling it a value, even though we know it's the value is J.K. Rowling. Value kind of sounds like numbers when you say it like that. So, anyways, sometimes it's good to write out little examples for these. Sometimes you can just think about it, and as long as you can explain why it is or isn't using like the context of the problem, then you're good to go. Like for example, number one, this is a function because each person has only one weight. Number two is a function because each number has exactly one square, so on and so forth. So for graphs, this is pretty important. I don't really know how to emphasize enough how important it is that graphs are just representations of functions. But like, if I asked you that what axis this was, you would probably say it's the x-axis. If I asked you what axis this was, you'd probably say it was the y-axis, and that's fine. But really, x values are domain values, and y values are range values. And the domain is like the input. It's like what you're like, for example, range is the output. Like up here, the domain was the people, and that's like what you start with. You're like, here's a person, how much do they weigh? And the input here was, here's a number, what is it square? So it's like the input is the people, the input is the numbers, the input is the author's name. And then the output, or the thing that the function gives you back, you say, here's a person, and the function says they weigh this much. You say, here's a number, and the function says, here's a square. You say, here's an author, the function says, here are some books that they wrote. But it's like the input is the domain, and the output is the range. The input is the people, the output is the weights. And so like domains and inputs are the same, ranges and outputs are the same. And on a graph, the x's that I graph are the domain values, and the y's are the range values. Because of the way we draw this plane, because of the way it was originally written, like these are always, when we're talking about graphs, we're always talking about numbers. The things on the x-axis are numbers. So if I pick a function, maybe I'm going to do that square one again. I'm going to pick the function that gives me the squares. So I would say something like, here's some inputs, -3, -2, -1, 0, 1, 2, 3. So I've determined that these are going to be the range values, sorry, the domain values. And then the function, which is like the squaring function, that's the one I've decided to use here, means that the outputs, right, domain is these numbers here. The x's, the domains, the inputs are these numbers, and the y's, the ranges, the outputs are what the function tells me. And if I'm using the squaring function, the function here tells me -3 squared is 9. -2 squared is 4. -1 squared is 1. 0 squared is 0. These are going to be the same. And I'm going to write them again because I'm going to graph these as points, which means I need like a coordinate pair for each one. Oops, I did that wrong. 2 squared is 4. 3 squared is 9. So I'm going to want to have a pair for each one of these. So I'm going to write 9 twice and 4 twice and 1 twice, just so I know that when so this basically says when x is -3, y is 9. You probably know how to graph that, but just to confirm, Negative 3 on the x means I go 3 to the left, and positive 9 on the y means I go up 9. Negative 2 on the x means left 2 and positive 4. Negative 1 to the left, up 1, 0, 0, 1, 1, 2, 4, and 3, 9. And then with these, if these are the only numbers I'm using, then this is the graph of the function. Y'all have probably in the past had teachers say, connect this with a smooth curve or something. And if I'm saying I want all the x's between negative 3 and 3, like I want negative 2.5, and I want a half, and I want 1.5, and all those, then you would draw a smooth curve here. The important thing to remember from this today is that the x's in a graph are the domain values. They're the inputs. They're the numbers that you give the function. And the y's, the up and down, are the range values. They're the ones that the function gives you back. And if I was going to write this function here, if I was going to be like, can we be a little more symbolic about this function? I would say something like the y values, which means like the up and down values, are the squares of the x values. So say something like y equals x squared. And then you think about it, that's how I got the y's. I squared the x's. And the function notation we would use, and you've probably seen this if you've taken Algebra 1, but we say f of x equals x squared. That x here tells me that whatever I put into the function, this tells me like f is the output and x is the input. So it's like saying whatever I want to input, I'm going to square it. So here my input was negative 3, I squared it and I got 9. For this line, the input was negative 2, I squared it and I got 4. For this one, the input was 0, I squared it, I got 0, and that's where the graph came. So it's a little confusing to think about, but really the functions come before the graphs, even though we kind of learn them in the other order. But that's just the way that is. So, and just perfect segue here into function notation. We would say here, the way you say this is you say f of x equals 4x. That's like how I would say that. If I saw that written and someone said, what does that say? I would say f of x equals 4x. It's important that you remember or understand that the parentheses here parentheses don't mean multiplication in this case. They have often in the past meant multiplication, but they do not today. And anytime you see this function like f of x, the functions can also have any names. Like it could be g of x, it could be h of x, it could be k of x, whatever. This does not mean g times x. I'm going to write that down because it's so important. Doesn't mean g, that's a really terrible way to write that. That looks like an x. Doesn't mean like g times x. Does not mean g times x. It means g of x. It's telling you that the function is named g and the input variable is named x. That's what it's telling you. F of x equals 4x means like whatever is in here, whatever the input is, the function is going to multiply it by 4. So if I said, well, what's f of 10? Well, that means whatever is in here gets multiplied by 4, so f of 10 is 40. If I say, what's f of 17 point, that doesn't look much like a 17. What's f of 17.5? Well, that's 17.5 times 4. 17 times 4 is 68, and then plus a half is 70, right? I think I did that right. Yeah, 70. But whatever it is, multiply it by 4. It doesn't matter what's in here. Always get multiplied by 4. And here's the more confusing one. And you're like, well, I don't know what the cosine of anything is at this point in my life. But if I told you that the cosine of 0 was equal to 1, and then I say, what's f of 0? You'd be like, all right. What that means is like, wherever the x's are in here, wherever the x's are in the function, I'm going to put whatever's in the parentheses here. So there's an x and there's an x. So unsurprisingly, they correspond to this one. So whatever's in here goes wherever that is. Just like up here, whatever was in there, we multiplied by 4. Here we're going to do 3 minus, there's an x there, so I put a 0. And then plus 2 cosine of 0. And it doesn't matter that if you know or don't know what cosine of 0 is. I told you it's 1, but it's just an example of a function. And so 3 is 3, 0 squared is 0, so I'm just not going to minus 0, it's not doing anything. And then this, I told you this cosine of 0 is 1, and 2 times 1 is 2, so it's plus 2. That equals 5 then. So here, f of 0 would be equal to 5. So this was a pretty simple function. This was a more complicated one. And you might be able to, if you like thought about what some x's were, you might be able to graph this one. This one would be more difficult to graph. I know that one point on the graph of this function is going to be the point 0, 5. I know 2 points on the graph of this one already. 10, 40, and 17.5, 70. Because when I put 17.5 as my input, like my x, the output, or y that I got was 70. So 70.5, 70.5, 70, 70. So it's going to be important that you can connect the inputs of functions to the x's on graphs and the outputs of functions to the y's on graphs. And we'll see more of that later. So here's just some examples which I can run through. This is a not too terribly complicated function, negative 4x minus 4. And then here's f of 0. So this just means you put the 0. You see there's the x is in parentheses and the 0 is in parentheses. So you just put the 0 wherever the x was. Negative 4 times 0 minus 4. Negative 4 times 0 is 0. That's negative. So 0 minus 4 is negative 4. Negative 7, again, whatever's in the parentheses goes where the x was in the function. So negative 4 times negative 7 minus 4. Negative 4 times negative 7 is 28. So that's 24. 5a, well, that's kind of annoying because it's not a number this time, but it doesn't really matter what's in the parentheses. The function tells you exactly what to do with it. It says negative 4 times the thing in the parentheses minus 4. So I do negative 4 times the thing in the parentheses, which in this case is 5a, and then I do minus 4. Negative 4 times 5a is negative 20a, and then minus 4. And then you're like, well, now what? And the answer is nothing. You're done. You can't simplify this. There's no like terms in that expression, and you don't know what a is, so you can't substitute anything for it. So this answer to this is going to have a's in it, and you kind of know that because there's an a in here. This number 4 is very similar. The thing in the parentheses now is a minus 4 instead of just a single number or a single variable term, but that's okay. The function tells me exactly what to do with it. Negative 4 times the thing in the parentheses minus 4. Negative 4. The thing in the parentheses is a minus 4. And then minus 4. Negative 4 times a, I'm going to use the distributive rule, which we're all familiar with. Negative 4 times negative 4 is positive 16. And then a minus 4 at the end gives me negative 4a plus 12. That's a 2. Let's imagine that's a 2. Negative 4a plus 12. And then this is like a joke. It's not really a joke, but it's like the point is to emphasize that it doesn't matter what's in the parentheses when you're evaluating these things. You just do whatever the function tells you to do with it. Here it was a minus 4, here it's 5a, here it's negative 7, here it was 0, here it's pickle. Okay. Negative 4 times pickle minus 4. Negative 4 times whatever's in there minus 4. That's what this function does every single time. Here the answers were numbers. Here the answers had variables in them. Here the answer doesn't make any sense, but the point is not that we're supposed to be like solving important math problems with this. The point is that this function does the same thing no matter what's in the parentheses. All right, I'm going to break this video here, and I'll probably post another one with the rest of the notes on it. But I just wanted to give you guys a little taste of where we started.